Thank you, Rudy. Thanks to the organizers for giving me the opportunity to speak here. It's very nice to be here. Great place. Really good to see all these nice people around. And yeah, I mean, every talk should contain a joke, of course. And like my joke is right away here. Like I made a typo while preparing this talk, and you can see it's not 21, of course. But the subject is new. You know, it's not like I'm giving a talk I gave 2 years ago. So first time ever I'm giving a talk about this topic. They just copy pasted the template, and then yeah, that's well. I checked the titles last night. Didn't do a good job. So I'll talk about this chromatic congruences and Bernoulli numbers. So it's some sort of a connection between group theory and number theory today we will be talking about. And well, kind of group theory and invariance of groups I need is something called orbifold Euler characteristic. And I need to also tell you what kind of groups I will be looking at today. So mostly it will be a discrete group. Actually, all the time it will be a discrete group. Sometimes it will be finite, but majority of times infinite. And we need some conditions on this group G to define some kind of invariance. For example, this Euler characteristic. And well, there are many different variations of these conditions, which I will describe now. But well, one condition I will be always assuming is that it's virtually torsion-free. So what does this mean? This means that there exists a torsion-free subgroup, some lambda in G of finite index. Pretty standard condition that very often holds in geometric group theory as well as in other areas of mathematics. And the other thing I need is some kind of finiteness property for this group, some kind of a geometrical finiteness, which is also a very familiar condition for many people probably in this audience. The exact condition I want to work with is that there exists a finite GCW complex model for the classifying space with proper actions E under bar G. Now, if you don't understand what this means, well, I can tell you this informally. So the G is acting on some kind of very nice complex such that the quotient is compact. Basically, that's what I'm telling you. And in this talk, the only thing you will need is the existence of such a space. So this geometrical finiteness somehow is just a condition we will need in this talk. We will never need an explicit model for this in the bar G. Because of this, I will not go into details. But if you want formally to know what it is, well, what is this thing? Well, it's a GCW complex. It's built out of some kind of equivariant cells. So it's a CW complex like in your algebraic topology class, but together with some kind of like posets, and then you just glue these things together. And then you have some prescribed behavior on fixed points. So if you take fixed points with respect to finite subgroup, then it's contractible and empty otherwise. So this is the E under bar G. And now I don't want to list all these examples, but a lot of groups in geometric group theory have this property. They have this, yeah.
So this implies, Victor, that EG itself is contractible.
That's right. Yeah. Yes, that's right. That's right. Because of the trivial sum. Yeah.
I have a question. How far? So what about one? How if the group is virtually torsion-free?
Yeah.
How close is this to having that finite index subgroup just have a compact EG?
Well, you can have a torsion-free group, of course, with a non-compact PG, right?
Right. Yeah. No, I'm saying if you have one though, like that seems like a weaker condition. But that's.
Oh, you mean just that has a yeah. So that's right. So actually, that's a very good question. So there is a difference between finite E under bar G and finite VCD.
Yeah.
And so VCD usually is strictly smaller than the minimal dimension of this E under bar G. And so I was telling you this in the bus, I think, that like if you pass to some kind of spectra kind of world, then what you are saying is exactly equivalent to having a stable homotopy type of this thing being finite. It's the same thing, yeah. Yeah, so it's stable and unstable difference, basically. Yeah. Thank you. So this is the under bar G, and many examples in group theory have this under bar G, and they are all very interesting. Like, I don't know, things like symmetric spaces, for example, and for L-Ser compactifications of symmetric spaces and things like that are examples for arithmetic groups, or some spines of dipolar spaces are examples of mapping class groups, etc., etc. So it shows up a lot in geometry. So soon these conditions just will be some kind of a black box, and we will be using it, and you don't have to worry much about it. Okay, so I'm looking at nice groups, let's say. Okay, so now let's define this Euler characteristic. So this is due to Wall, and what Wall did is that, well, first of all, you need to recall classical Euler characteristic. Well, that's just the usual rational cohomology of groups, and then you take the alternating sum of the dimensions of any universe. And then if you want to define the orbifold Euler characteristic, what you need to do is you need to take the torsion-free subgroup of finite index, the one we mentioned in the previous slide, and then you define this invariant like that. It's a rational number. So you take the integer, which is the usual Euler characteristic of this torsion-free subgroup, and then you divide it by index. So this is a very well-known invariant due to Wall. So maybe I should have explicitly said here that it's a rational number, but it's a rational number. Okay, so and then it's well defined under our conditions. That's the main point why I asked for these conditions. It's one of the standard conditions that makes this thing well defined and independent of the choice of lambda. Okay, because you can take some other finite index subgroup which has a different index, but it turns out it's the same thing. It's a very nice, well-defined rational invariant, and well, immediately you can see that there are some amazing examples and very nice relation to number theory of these invariants. Well, let's start with a special linear group SL2 of some numbering OK. So K here is a totally real field. I don't want to define what a totally real field is, but you can think of it like, for example, real quadratic field, square root of 5 or something. And then OK denotes the ring of integers. For example, Z for Q or something like that. Okay, so then what Jutta Harder showed is that if you compute orbifold Euler characteristic of this group, it's the special value at -1 of the p-adic zeta function of this field K. So it's a very interesting example immediately, and also by the way, the underbar G for this example is a well-known thing. It's called Hilbert's modular surface. Actually, that's actually B underbar G. It's the space whose quotient is the Hilbert's modular surface.
H2 cross H2?
Sorry?
H2 cross H2.
Yeah, exactly. But not the co-compactor, right? Okay, you need to find the spine there as well. Yeah, it's always the spine gains or a compactor file. Okay, so then you can also look at symplectic group. In this case, again, Harder showed, Harder in general put the formula for arithmetic groups, that if you take the orbifold Euler characteristic of symplectic group, that's the product of special values of negative all the numbers of the Riemann zeta function. Okay, so you see now this example is also very, very interesting. And maybe I should mention also the mapping class of the surface of genus U, gamma U, and well, you can blame me now. Why am I not using genus G, like the G for the genus, letter? But I have so many G's afterwards in this talk as elements of some groups that I better use a different. So it's G. Really I thought long time ago, like, what should I use as even in my paper, like for the genus, and I finally came up with U, and I like this. Okay, so this is the genus U surface, and so what Harer and Zagier proved is that if you take orbifold Euler characteristic of the mapping class group, there's the special value of Riemann zeta function for the negative ones divided by 2 minus 2u. And some people maybe only remember the special value of the zeta function, but in that case, you need one marked point. Without marked points, then you have to take into account fundamental group, and that's what shows up in the denominator. So that's the formula in the non-marked group case.
So in these theorems, what they were interested in, the zeta function or the Euler characteristic?
Euler characteristic. They were interested in some kind of Gauss-Bonnet style theorems, actually. And that's what it gives you somehow, the consequence of these Gauss-Bonnet style theorems for these kind of like orbifold quotient kind of things. Yeah.
So I guess it does give you rationality.
It does. Oh yeah, I will be discussing this now in a second. Yeah. So I'm going there. What it gives us in number theory, that's the topic of today's talk. Yes. Right. So and this B2U is of course 2U to Bernoulli number. So that's the Bernoulli number. Okay, so because I will be talking a lot about Bernoulli numbers, let's make a quick survey of Bernoulli numbers. So it's defined using Taylor series, like that. That's the exponential power series. Yeah, so let's look at some values. As you see, at the beginning is the denominators that are big. And by the way, odd ones always vanish, right? Like except the first one. That's just a fact. And as you see at the beginning, it's the denominators that are bigger. But once you go a bit higher, denominators actually stay pretty small and the numerators explode. Like numerators become huge. Like you can go to this list of values of data functions and you can see that at some point, like numerator is this big and denominator maybe this big. Right? So it's pretty clear. But I will now say a theorem which actually explains this in some way. Okay, so a fun fact just to tell you how Bernoulli numbers were discovered. I mean, yeah, people were trying to compute the sums of these powers. That's how it was originally discovered. By Bernoulli and by some mathematicians in Japan as well, and I think some other people. Even before Bernoulli, they had some ideas about it. Anyway, so that's Bernoulli numbers for you. And well, important fact, of course, is this one as well, that special values of Riemann zeta function with negative odd numbers can be expressed in terms of Bernoulli numbers. That's what I'm using in this formula. Okay, so that's Bernoulli numbers for you. Now let's go to what's the relationship between this orbifold Euler characteristic I defined and what does this give us in number theory? So now the first instance of using this kind of like orbifold Euler characteristic in number theory. Okay, so a subgroup E is called elementary abelian P subgroup. Well, it doesn't have to be a subgroup. I can just define elementary abelian P group. But anyways, I did this for the subgroups. So a subgroup is called elementary abelian P subgroup if it's isomorphic to a product of some Zeeman P's. Okay, that's a very well-known definition. And then this R is called a rank, like a vector space dimension, whatever you want. But it's a rank. Okay, so now what Brown showed is the following congruence. So suppose G is a virtually torsion-free group with finite under bar G, the conditions I assumed at the beginning, and assume that any elementary abelian P subgroup of G has a rank at most 1. That means there is no Z mod P cross Z mod P inside my group, okay? So then what Brown showed is that the following congruence is true, that if you take orbifold Euler characteristic of G, it's the same modulo P local integers as the sum of centralizers, orbifold Euler characteristics of centralizers, index of conjugacy classes of non-trivial order P elements. Then this factor 1 over P minus 1 shows up. That's actually automorphism group of Z mod P, actually. That shows up, yeah. So this is the congruence, like what Brown obtained. And Brown obtained this using like analysis of all these like posets of subgroups and lots of like homotopy theoretic or homological methods with respect to posets and things like that. It's quite an involved group. But well, it turns out that it's pretty useful in number theory. So just to recall that a rational number is 0 mod ZP means that there is no P in the denominator of A, okay? So that's why it needs to be 0 modulo ZP. Or two things are congruent modulo ZP if and only if they have the same P fractional part. That means if you take partial fraction decomposition, the part that has the P power and the denominator are the same. Okay, so that's what it means that these two things are congruent from P. That means that whatever the P to the power denominator left-hand side has, the same is to the right side. So we basically study what are the powers of P in the denominators and what are the numerators of those. Okay, so that's Brown's congruence. Now, before I tell you what Brown's congruence give us, I need to recall a quick fact about Bernoulli numbers, which is called von Staub-Lausen theorem from 19th century. That says the following thing. So if P is a prime and P minus 1 divides 2U, then this sum is congruent to 0 modulo CP. And that is explaining a bit what I was talking about before. So you see that in denominators of Bernoulli numbers, multi-squares show up. It's always simple factors for every prime. So you take a prime decomposition of the denominator of Bernoulli number, it only has 1P there, multi-square. In fact, Untitled is much more general. I'm just talking here about the p-local version of it. So there is a more general form of this theorem. I just only need a p-local one. This is why I formulated it this way. That's what experts in number theory do. Okay, but numerators can have any powers, So that's definitely possible. So now I was talking about this congruence of Brown and explained to you some basic properties of Bernoulli numbers. So finally, I can tell you what Brown used this congruence. Okay, so what Brown did is looked at groups that satisfy the conditions what Brown asked for, which was the rank of elementary abelian p-star groups is at most 1, right? So SL2 of OK, OK totally real satisfies this, because every finite sum is cyclic actually. So there is no Z mod P cross Z mod P there. The other group is the symplectic group, for example, when P is a mod prime. It also doesn't have Z mod P cross Z mod P inside there. It's very easy to see in these cases. Okay, so, well, I don't want to go into SL2 OK example much, but I can just tell you that what Brown did is that looked at special values of the p-adic and zeta function, and using this congruence, obtained some new results about the p-fractional parts of this special value zeta function. But I didn't completely compute it, but at least said some new things about it, which are probably best results until today about this kind of congruence, using this congruence. Okay, so that's just the story. Now let me give you a more detailed analysis what happens in the case of symplectic group. Exactly write out what this Brown's congruence is in this case and what kind of number theoretic consequences does this have. It turns out that this is not new. So Brown rediscovered some results due to Kummer and some other people that were known from 19th century. Okay, so let's recall the class numbers. So HP denotes the class number of the cyclotomic field with the zeta p, the primitive p root of unity. And what Kummer showed is that this plus number decomposes as a product of two other numbers, where HP minus 1 is called the first factor and HP plus 1 is called the second factor. Well, good names. And then HP plus 1 is also the class number of the maximal real something. Okay. Now, why am I recalling this? Well, turns out that this can be used to describe conjugacy classes of order p elements in this symplectic group. There are exactly these many conjugacy classes of order p elements. So this first factor of the class number shows up in this classification. This is due to many people, and I don't even want to mention names. So what are the centralizers? If you take Z mod P inside SP minus 1, it's always true that the centralizer with that is ZP cross Z mod 2. It's the scalar matrices that show up like it's additional part in the centralizer. Okay, so then what does Brown's congruence tell us for this symplectic group? So I go back to this congruence, which one was it? So it was this congruence here I'm talking about. And what this congruence gives exactly in the case of symplectic group, you can see it here. There you go. So that's what Brown's congruence exactly translates to in the case of symplectic group. So the product of these special values of zeta function is the same as this class number times this kind of thing. Well, people who know number theory probably recognize that like the class numbers and zeta functions are very closely related by class number formula. So it's not like some shock here that happened in some ways. But the cool thing is that actually you rediscovered this formula thanks to Harder's result and Brown's result. You rediscovered this congruence, which actually Kummer discovered in the 19th century using small elementary methods, of course. But you already discovered some number theory in the simplest possible example, which is the symplectic group, which is kind of funny. Okay, so what are consequences of this congruence? Why should we care about it? Well, let me tell you this as well. So consequence of Brown's congruence for this symplectic group. Well, I'll recall this congruence again. So this is how it looks like. This recovers Kummer's regularity. So again, uses this von Stahl-Clausen theorem I was talking about. Now, Kummer's regularity says the following thing. An odd prime does not divide the first factor HP minus 1, so this first factor of the class number, even only if he does not divide the numerator any of these Bernoulli numbers. I intentionally skipped the P minus 1 because that's exactly this von Stahl-Clausen taken care of by von Stahl-Clausen. I can remove that, and then I only care about these. for the divisibility of HP minus 1. So this follows from this congruence. It's an obvious elementary exercise out of this congruence. I mean, you can do it yourself if you want, yeah, but maybe you should listen to talking to others. Okay, so then why were these regular primes important? Well, Kummer managed to prove Fermat's last theorem for the powers of these regular primes. That's why these regular primes were important. So this was the first instance when someone proved Fermat's last theorem for infinitely many primes. So Kummer did that in one of his papers. So that was for regular primes. This is why at some point there was a big hype about, oh, are there infinitely many regular primes, blah, 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 all these things. And so it turns out there are, and this is why these congruences are important. Okay, so fun fact, if you want to talk about divisibility of the other factor of the class number, that's a very complicated problem. So I'm talking about here divisibility of the first factor. So if you go back to this slide, you see that the class number here, it has two factors, and the HP minus 1 is usually easier factor, and I'm telling you some things about it. If you want to tell me something about the other factor, well, that's Kummer-Van diagram conjecture, equivalent to for some people here who don't care about my talk, but only care about homotopy theory and algebraic K theory. There you go. So this is equivalent to for n algebraic K theory of integers vanishing for after 4, 8, etc. All the multiples of 4. Yeah, so that's why this type of congruences and divisibilities are very important to study. Okay, so that's what happens for the symplectic group. So a symplectic group is a very simple example. I go back again to the slide where I was looking at this example. You can completely classify order P elements. There is no order P square elements. Centralizers are super easy. And even in this easiest example, we discovered some super classical number theory, which is due to Brown, of course, but it's tells you how powerful this machine potentially could be to discover some new results. Well, Brown showed that it was very useful because it did something with this data and zeta functions, but I don't want to prove it. Okay, so that's consequences of Brown's congruence. Now we need more congruences here. So next one is the Brown-Quillen congruence. Why do we need this? Well, what's the point? Was not that already good enough? So the problem with Brown's congruence is that the condition that any elementary abelian subgroup of G has a rank at most 1, which I asked for Brown's congruence, is just too restrictive to get more applications in number theory. So we have some arithmetic groups and things like this in number theory, and if we start using these orbifold Euler characteristics, then maybe we are discovering some new results in number theory. But very few interesting groups satisfy this condition. Sorry to tell you this, but this is how it is. Okay, so, well, what should we do? We have to remove this condition, right? And that's what Quillen actually did. So Quillen did this. Is one of the last parts of Ken Brown's cosmology of groups book. Brown writes that this theorem is basically due to Quillen, but then he writes up the proof. So because of this, I call it Brown-Quillen congruence, because I did not see in literature anybody calling this thing any names. Because basically this result is somehow a bit forgotten. Haven't seen a paper after that talking about this result, to be honest. So the Brown-Quillen congruence is the following thing. Again, G is virtually perfectly good with finite the other G. The condition I asked at the beginning. And so this is what you get. So you get that you have this congruence, orbifold Euler characteristic of the group G plus a sum indexed now on non-trivial elementary abelian P subgroups, conjugacy classes of those. The rank shows up. This binomial coefficient shows up in the power of P. It's not a surprise because I think this is some kind of order of a CELO subgroup in GL whatever of CMOD P. I think in GLN of CMOD P, the CELO subgroup is order P to this binomial coefficient. So that's why this is there, just to explain to you where it comes from. And then this normalizes. So now you have this congruence. R is a rank and N is a normalizer. So this in particular generalizes the previous congruence. So in particular, if the group satisfies the condition that every elementary abelian P subgroup has a rank at most 1, then you recover Brown's congruence. And now the proof of this result was actually very, very non-trivial, because uses the Solomon-Kitz theorem, and also all these Quillen style arguments about the process of elementary abelian subgroups, like homotopy theoretic analysis of this, and the fact that it kind of looks a bit like Kitz building style thing, that it's a wedge of spheres and things like that, so up to homotopy. So this is some geometry involved in this, geometry of the process.
Wasn't Brown's theorem saying there was centralizers, right?
Well, you can easily translate between those two, because normalizer modulo centralizer is finite, because it's always a subgroup of the automorphism group.
Yeah.
And and because it's finite, the orbifold Euler characteristic of normalizer is equal to the index times, or 1 over the index times the subgroup. Because this orbifold Euler characteristic is well behaved with respect to index. So with changing the index, you can immediately translate between centralized and. So because of this, you're going to recover Brown's theorem. Okay, so that's the history of this theorem. So this theorem is not so explored. I have to say, I haven't seen a single, like I told you, some applications in number theory of Brown's congruence. I haven't seen any single application of this theorem in number theory so far. And I was surprised why. I mean, again, not so explored this formula. Well, my guess is that it's difficult to classify these conjugacy classes of elementary abelian subgroups and their centralizers or normalizers. I mean, it's not an easy game to play. I mean, if you have some serious group like arithmetic group or something doing this, very difficult task. With the order P elements, it still kind of works. Well, with the elementary abelians, it gets tricky. That's why it was not so explored. So now, today's talk, finally, right into the after all this history and right into the moment when I can tell you what I'm going to do today's talk. So, well, I'm going to tell you, yeah, question. Now, maybe it's a good point to actually ask questions, because I finished the history, so I can now go to. All right, so what I want to tell you something today about is new congruences for n prime p and n. This only will depend on the conjugacy classes of finite abelian p subgroups, not elementary anymore. But condition is that it's generated by its most n elements and their centralizers. So in particular, n is equal to 1 will only require secant p subgroups. So that's what I'm going to tell you today. Well, in a second. And when I take a limit when n goes to infinity, so I have these congruences for every p and every n. And when I take a limit when n goes to infinity, I will recover the Brown-Quillen's congruence. So what I'm telling you is that there are actually way more congruences than what Brown and Quillen discovered. So you don't have to talk about elementary abelians. You need to only talk about them when you go to the limit with n. So now, depending on what the situation is, you can play some game and change this n as you like, as you wish, depending on the group. So main example I will apply this afterwards will be the mapping class group of the surface of genus U. Funny thing is that Brown did his applications in number theory sometime in the 70s, and then Harer-Zagier discovered this connection in the zeta function of the orbifold Euler characteristic of mapping class in the 80s. And nobody since then tried to apply Brown's techniques to the mapping class group to actually get some results out of it. And in some ways, this is what I'm trying today. But on the other hand, I could not apply Brown's result, because Brown's result requires that every subgroup every elementary abelian subgroup is rank 1. For this mapping class group can have any rank, any finite group, as Andy also explained to me in the bus how to do this. Any finite subgroup is any finite group is a subgroup of a genus U mapping class group. Big enough. So any of these Z mod PNs or Z mod P to the N's can show up here. So these congruences of Brown and Quillen or Brown will not help you to say anything about mapping class. We also have way more finite subgroups here than just Z mod P. And classifying these things in mapping class groups is very tricky business. Broughton has done some classification of these kind of things, but then you also need some things about centralizers, normalizers, and well, it gets very complicated very soon. So but I think using these congruences here, you can say quite a lot about mapping class groups as well. Okay, so let me state what this congruence is. I call it chromatic congruence at height n, and I will explain why. It's not just a name for fun, it has something to do with stable homotopy theory, chromatic stable homotopy theory and formal group theory. Okay, so commuting tuples, this is something I need to define for you. So this is the very good helping device in this business. So you take this n tuples of commuting elements where each of the elements have a order of power of p, like p to the square, p to the 3, p itself, trivial, if you want. All these things are good. So and n stands, of course, for the size of these tuples, and p stands for the which powers I'm looking at. And then G is acting on this thing. So G acts by conjugating in each coordinate, right? I mean, I can just conjugate every coordinate. It's a very nice G set. Not necessarily finite, but if you take a quotient, it will be finite under my conditions. I'm asking some nice finiteness condition on the group, and if you have a finite under RG, the condition I asked for, then there are only finitely many conjugacy classes of finite subgroups. So that immediately guarantees that the quotient of this thing is finite. I should have maybe written this down, but I got it. Okay, in any case, so this is the theorem which I managed to somehow observe. It's not a difficult result. So if you take p a prime and n greater or equal than 1, and so assume that G is like satisfying all these conditions I was asking, then you have this kind of congruence where you first look at the orbifold Euler characteristic of the group, and then you look at all these kind of tuples. As I said, there are finitely many of them. This is the quotient. Take all these kind of tuples, commuting tuples with p power order elements, take orbifold Euler characteristics of centralizers of subgroup generated by this tuple. And this is congruent to 0 modulo ZP. Yeah.
I mean, if you take G1 up to Gn is equal to 1, 1, 1, 1, don't you just get G as a centralizer?
Yeah, this is why I removed it from here. You see?
Why not just having a big sum?
Well, I want to always make a point that I'm trying to figure out this, and then I'm trying to find it with smaller things. But I could have done it. This is how I do in my paper. Thank you.
So what is the sum going G over?
Oh, this is the quotient of this thing by G action. You take equivalence classes of this by conjugation.
Yes.
And then you remove that 1, 1, 1. Because I want this thing to be grouped here separate, you know? Yeah. And that is congruent to 0 mod CP. Okay. So I'm saying something about the fractional part of this in terms of this.
This way and equivariance characteristic.
Sorry?
This is an equivariant characteristic.
No, I don't think it is that, because that one does not talk about p power elements. That talks about only commuting elements. That's right. Yeah. So here I'm just, this is actually more K theoretical characteristic. Actually, I'm writing a paper about that, which soon will be out. That if you put these p powers there, I will just talk about that in the second lecture. Yeah. So the equivariant, anti-equivariant, talking about just its all commuting elements, but that will not give you here all these p local results. Yeah. Right. So now, why do I call this chromatic congruence at height n? So maybe I should explain this. Well, I don't know if you want to see much of the proof, but well, maybe I'll quickly tell you the proof as well. Like, proof is that you can actually show that this sum can be written as this kind of sum. This is an idea of Quillen, basically, goes back to Quillen. And this sum is indexed over cells of the C under RG, and these are just all these isotropies that show up in the C under RG. This kind of alternating sum. And this is how I actually guess this congruence. I mean, I was doing something completely different, and then suddenly I stumbled upon this formula, and I suddenly realized that there is something called Frobenius. Well, Frobenius' theorem, not the Frobenius map. So if n divides the order of finite group H, then the number of solutions of the equation xn is equal to 1 in H is multiple of n. That's a fact. And using that fact, you can see that these fractions here are always p integral. So I was doing something else completely different, and then suddenly I was looking at this, and like someone was calculating some examples for this formula. I didn't think it was has any significance in some ways. Realized that these things were the integral, and then I knew that there was some kind of congruence going on, like this. So that's the proof basically of this result. Like as simple as that, but you just need to observe it. I mean, this fact holds is a bit of a work, but again, that's like some standard arguments using some Maya-Vitori style observations, because you need to talk about some sort of the compositions of these and then how these Euler characteristics behave with respect to that. And that's some Maya-Vitori statistics. Okay, so that's an observation. So why chromatic? Well, where did this whole thing come from? So Hopkins, Kuhn, and Ravenel actually have used this commuting n tuples of p power elements a lot in chromatic stable homotopy theory. So the H is finite, and if you take morality theoretical characteristic, answering your question, well, morality theoretical characteristic of this group H, then this is the cardinality of that. So I'm actually, for these type of groups I'm talking about today, very soon, hopefully sometime in a couple of months, well, there will be a paper out which also computes this for these type of infinite groups I was talking about today. I'm talking about today, and this thing shows up in that calculation as well. So these commuting tuples of p power ordered elements are showing up in the nth level, height n level of chromatic stable homotopy theory like this. And this height, of course, here means the height of the formal group law, because these Morava K theories have the height n formal group law, the so-called Honda formal group law in there. So this is why I thought it's a good name to call this congruence the chromatic congruence at height n, because they actually are directly related to the Morava K theory. Okay, so, well, that's the proof, and that's the explanation why I came up with this name. Okay, so then, now, even a more numerical way of dealing with this congruence. So I want to make it even more explicit, like make it more evident somehow to apply to number theory, this kind of congruence. So, well, it's so far still a bit tricky, like how are you going to compute this quotient? What do you do with these things? Well, there is a way of doing it. It goes back to Hall, Philip Hall, that did some Möbius inversions to study whole sets of subgroups in finite groups. And later, by some people in random group theory and things like that, we're using also this combinatorics a lot for some kind of Markov chains like diachronics and some others. So you need to analyze generating tuples. So what's a generating tuple? So if you take H as finite abelian P group, then this gen n is the set of generating n tuples of H. So like, you know, take those tuples that when you generate a subgroup, you get the H. Okay. And what Hall did is to give you a formula for these generating n tuples. So if you do this generating n tuples, this is this huge formula. It can be proved using some Möbius inversions. Well, this phi H is the Fratini subgroup. So the minimal one whose quotient is the elementary abelian. This is the p binomial coefficient, which is like a binomial coefficient, but with the power of p. And this is some stuff, some rank of distinction now. Well, it's a very explicit formula. And now you can use this formula to, instead of talking about the quotient of commuting n tuples, you can use this formula to actually completely translate that into some kind of number theoretic stuff using this kind of generating tuples. And well, you can reformulate the theorem I just was talking about. Theorem is that we have this congruence. So it's the same congruence I was talking about before, but I just made it explicit and got rid of those commuting n tuples by actually telling you how to calculate them. And you calculate them using this Fratini subgroup, and now the sum is indexed over conjugacy classes of finite non-trivial abelian P subgroup generated by at most n elements. And this is way more explicit formula. You can directly, if you know normalizes, write out the congruence using this. Okay, that's the thing you get. Well, that's really good. What does this bring us? Well, let's see. Well, it brings us first of all that there's some numbers and some funny formulas going on, but like that's not good enough probably. So what happens in the limit? We can take n goes to infinity, the limit. Well, how do you do that actually? Well, we should do it in p-adic world, not in the real world, because in real world it's going to be infinity. But in the p-adic world, a lot of things here will become zero because these are all powers of p here. So if you go to p-adic limit, Then, and the use that Fratini subgroup is trivial, even though if you were elementary abelian, well, you're going to rediscover the Brown-Quillen congruence as a limit of this stuff. So we go into the limit in this formula. That's the formula I had before. I just went into the limit, p-adic limit. Well, the p-adic limit turns out to be exactly the left-hand side of the Brown-Quillen congruence. So that's what I was telling you, that I will have some congruences today. If you go to the limit, when it goes to infinity, I will rediscover what Brown and Quillen did. Well, proof is elementary, as I told you, like you just elementary p-adic analysis. Yeah. Okay, so, and well, of course, the congruence itself, how does that follow? I mean, the limit is a rational number, we know, but these terms are p-local numbers. So that means they are also p-adic numbers. So I'm taking a limit of p-adic numbers that will stay a p-adic number. It will not become a p-adic rational. It will stay a p-adic integer. And the unit is in the rationals, right? So because of this limit is rational, but at the same time, it also stays in p-adics. Well, that means it also belongs to p-local integers, and because intersection of rationals and p-adics is p-local integers, and you recover the Brown-Quillen congruence. So now we have a congruence, rediscovers all these Brown-Quillen results that was used in number theory. We have way more of them than before. We have like whole infinite family of those that in the limit give you the ones that were known before. So how can we use this? Is there any application for this stuff? And that's where you go to mapping class group. I was really looking for a group where I could apply some of these formulas. And I mean, everywhere is so complicated to classify even cyclic subgroups inside your group. It turns out that Harer-Zagier have done everything what I needed to directly plug in mapping class group in this formula. And let's see what we get. Well, Harer-Zagier, this is what they did. It's good that you can see actually this formula. So, well, I'm not expecting now from you that you will understand this formula, but I will at least give an idea. So what Harer-Zagier did, they just computed the usual Euler characteristic, rational cohomology Euler characteristic of the mapping class. And it's this huge, whatever formula where you have this n as well, which is the cardinality of this kind of funny set. If you really compute this, it involves some Möbius functions and Euler's functions and like it's a big formula. But the funny thing here is that this K corresponds to order K element in the mapping class. So in some ways, you know something about some, and these numbers are exactly that come up from the orbifold Euler characteristic of centralizers and normalizers. So basically, you know the sum of some kind of orbifold Euler characteristics of centralizers, which are indexed on elements of order K. So that's basically what they did in the mapping class case. So, well, I stared at this formula and I realized that if I apply this chromatic congruences I was talking about before, the height 1, just 1. So no commuting tuples, just order P power elements, so cyclic P subgroups. And you really stare at this formula, you realize that if you pick out from here only powers of K, then you get a congruence, mod ZP. And that's, here you get an integer, but you have way more Ks. Some of them have even mixed prime factors, but I'm telling you, you don't worry about all these P factors that have P inside, but have some other primes as well. You can throw them out. And what you get is this kind of congruence, modulo ZP, you get this kind of congruence where only primes of the prime powers stay around. So the orbifold Euler characteristic of this thing, which we know is this data function, values of data function in Bernoulli universe, plus some stuff is congruent to 0. So this is exactly this congruence which I proved for you today for n is equal to 1 and prime P. Okay, well, what does this buy me? Like, it's a big formula and I couldn't do anything with it before. I can't do anything with it maybe now. Well, it's something, some Bernoulli numbers are in here to satisfy some stuff, but well, what can we do? Well, it turns out that lots of terms here are already integral. If you really do your homework, I was doing 2 months that actually sitting there, just simplifying some terms for 2 months. Literally like school mathematics, you know, like when they give you this big expression like, let's simplify this polynomial or something like exactly this type of mathematics, you need to go through all these things. So you get something in number theory out of these congruences. And I can list now the results which you rediscover in number theory using this whole business. Okay, so well, this formula is tricky, but this formula reduces to the following results. It reduces to some classical congruences for Bernoulli numbers. And for some time, I thought I discovered some new congruences for Bernoulli numbers. And almost 2 months, I thought I discovered some new congruences of Bernoulli numbers. But then I met someone, I forgot who it was like, maybe Marcus or someone like, are you really sure you're saying something new about Bernoulli numbers? They have been studied for 500 years. And they were right. I think he was human. You told us that. Well, you were right. So we discovered that this chromatic congruence, what I talked about, that height n is equal to 1, for mapping classicals recovers many of the classical congruences for Bernoulli numbers, which have been proved in the last 100 years, I have to say. It's not just the one that Kummer discovered. So the first one is, of course, the standard Kummer's congruences. So due to Kummer, and the original result is due to Kummer, and then the modern form is due to Voronoi. So this says that if p-1 does not divide 2u, and then there is this other condition, then you have this kind of congruence between these quotients of Bernoulli numbers. This is an extremely important result because this is the beginning of p-adic zeta functions. So this basically shows you that the p-adic L functions and the p-adic zeta functions can be defined. And this is some sort of like their continuity result, basically. So it's extremely fundamental in analytic number theory.
So you have no assumption B whatsoever?
There is no assumption on B except it's this. There isn't. Except B is that. And prime is always bigger than 5. There are some versions of prime 3 as well, but you know, there are some 12s showing up in this denominator, so I don't want to deal with that. Okay, so this is not all the Kummer's congruences. So Kummer never required that U looks like this and B looks like that. Kummer just asks that p-1 does not divide to U and does not divide B as well to B. Well, I don't discover all of the Kummer's congruences, but at least infinitely many of those using this formula. If you dig into this formula, what it gives you in this case is Kummer's congruence. The other one, I first actually wrote this down, and then in that case, some congruence came up. Then I searched it, and somewhere in the 50s, Carlitz, the famous number theorist, actually, was doing a lot of things about Bernoulli numbers, discovered this congruence. And you rediscovered this congruence as well using this formula. So for 2u like this, where p does not divide 2u minus 2, you get this congruence. Again, this is a special case of that big formula I was talking about once you realize that lots of terms are p-integral. That's what is left. Okay, now the congruence which I thought that I discovered, but it turns out I didn't. It was someone else. But it's a funny story. I'll tell you a funny story. So not so well-known congruence, I gotta say. I was searching for this for 2 months, really, like giving an effort, you know. Even wrote like Nick cuts in unit. He didn't know. So I was like, wow, maybe I really found something new. But then, what is the place where you're gonna find where everything is done? Not all. I actually, by Google searching, stumbled upon a message by Irakli Cohen, who said that there is this congruence, which is a version of Kummer's congruence. When you see the condition here, p-1 does not divide to u. What happens when p-1 actually divides to u? Well, one situation is this, what I told you. But what about in the case when also p divides this? So that's the question. So, well, Cohen is right, and it's not also, because by the way, there is this other version of Kummer's congruence when p-1 they divides this to u. And I have never seen this anywhere in the literature before. And I wrote up this in my book instead. So that is his 2007 book about analytic number theory. And well, it turns out that this was exactly the congruence which I discovered using this mapping class for years. Well, in fact, again, Cohen's congruence is more general than this because you don't need the u and b to look specifically like that. You just for any u and b where p-1 actually divides 2 times u, and 2 times V, this congruence is true. But in this case, you rediscover this congruence for these numbers. I mean, actually, you can easily see that V minus 1 in this case divides 2 times U. I mean, I don't want to write that. But in any case, so this is the congruence which I found. So, and it turns out that Cohen in 2007 also found it, but in a more general study. Well, Cohen uses, of course, the seriously p-adic L functions for this proof. It's not trivial proof, actually. Actually needs to do like whole analytic continuation and everything for these L functions and theoretical characters and everything before it gets to this congruence. Well, I mean, of course, we are using just geometry of the moduli space, but some other hardcore stuff, because like Harer-Zagier is a serious paper, so we are using that. But this is sort of like geometric way of seeing this formula. In any case, so this was what mapping class group gave us. So mapping class group will not give us anything more with these methods. So what we found now is that the mapping class group case rediscovers all sorts of well-known old congruences for Bernoulli numbers using this orbifold characteristic technology. The problem is that well, mapping class group is still a pretty good group for classifying cyclic subgroups. Now, what happens for the other groups? I do not know, and this is what we should discuss next. Okay, so let me just make all these congruences I talked about explicit for one particular mapping class group. So this is a mapping class group where a torsion is pretty simple. So you have only Z mod P's in there, no Z mod P squared. And there is only one conjugate class of Z mod P cross Z mod P. Only one congruence class. So in this simple case, I can actually write out all these congruences I was talking about today. I mean, I know they're small, but I don't know how to fit them in the one slide. So these are all congruences which we talked about today. So this chromatic congruence which I presented today, it takes this form in the case of this kind of mapping class group with all these powers of P and stuff involved. At height 1, this is exactly this congruence, which is equivalent to this Cohen's congruence I was talking about. You actually look at this congruence more carefully, you discover that this is exactly Cohen's congruence. This is the Brown-Quillen's congruence in the mapping class group case. And you see that it's very different. The height infinity case is very different than height 1 case. There is this extra summand here. And that comes exactly from the elementary abelian subgroup CP cross CP that is sitting there. Well, the difference turns out between these two formulas is again some number theory. It's again pushed out Walton theory. So these congruences at height infinity and say height 1 are essentially different because of some non-trivial result of number theory allows you to compare them, but they are not obviously the same. Well, for higher ends, they immediately recover again Brown-Quillen. So anyways, this is the only group I managed to actually make all these congruences, only mapping class group, I managed to make all these congruences this explicit because in other cases, I don't have this nice classification with other elementary abelian or subgroups generated by 2 elements classification. So Harer-Zagier did a great job for actually classifying or at least giving their information about everything I needed to write down my formula at height 1, which was not possible in the other case. But we will see where it can bring us in the mapping class group. So potentially there are more congruences for Bernoulli numbers if we can make all the congruences explicit at any height. But well, I don't know if I can manage that. So what's next? So just to give you a update about what's the next thing to do. Well, we can try to look at the symplectic group SP4 at the prime 3. This should say something about this product. And a lot of results are known about this, but not so many about this. Reason probably being that people like Brown, etc., did not really look at this group. Because, well, they had to look at all the elementary abelians here, but, well, now we don't. We can use this version, what I was talking about today, different congruence, which avoids both. Or the other one is the symplectic group. This is one I really want to do because I think this could give some funny results. Should say something about this product and plus numbers again. Maybe something similar to Kummer's regularity, but it will be something qualitatively different, I believe, because there's some other type of plus number that show up. So that's the next step, these two groups. So why these? I mean, they have no p-square torsion. So this chromatic congruence formula at height 1 at least will be very simple. It will only have zero in there. But they do have this kind of subgroups. And I don't have to worry about this kind of subgroups because I can use this congruence I was talking about today, so the chromatic congruence. So chromatic congruence at height 1 should be not too bad for these kind of groups. And I mean, it gave us something from epic class groups, as you saw, some interesting results that were known in number theory. So I'm expecting for these groups, if we make these congruences explicit, we'll get some new results in number theory that were not known before. But yeah, well, that's just a hope. All right, I think I'm done. Thanks. Yeah,
It's not like in the group is a torsion of the matrix.
that's right.
Something hidden.
Well, unfortunately not. Correlate is very tricky, right? And I mean, I think it's like to talk to India about it. And well, even we had this good discussion in the bus yesterday. So as he explained to me, even these two formulas, that there are these data numbers showing up for selected group and the data number shows up for the metric. Even these two formulas, somehow there is no explanation like how these two formulas are related in terms of this quotient. It's some miracle somehow. Yeah.
I think the real problem is the Schroeder group is the cohomology is infinite dimensional. So like there's no, you can't make Euler equations.
Yeah.
So
Yeah, I'm wondering if you took it SD2, so 2p squared, the 2p minus 1 down there to get really to rank 1 and 1. So there's negative. What happens if you down doesn't need 2p squared? And does it look like a B product or something? And you can still classify the elements or
where did you take p squared? You take S2p squared, symplectic. I don't remember exactly when the p squared torsion shows up, to be honest.
you might still be able to control
Well, already getting control of order p elements is some extremely non-trivial number theory. So anything you can do here, whatever methods, is already an interesting thing. So I don't know how to do that. So here my hope is that I will still just deal with the p torsion, no p squared, and I don't need to worry about the limit variability. So maybe somewhere in between there is some number theory needed. Yeah.
So there are, I'm not a very expert to ask this question, but maybe someone is. Like, there's a lot of analogies between master class groups and Aberdeen, and I've also worked with Gordon Free. So you could try and you know, and you have some idea of like try to figure this out. Try and put this into your.
I'll be doing this already. I've been doing this already. So I'm trying to. I mean, first of all, thank you for this question because orbifold Euler characteristic out of 10 is still not completely computed. I mean, Karen Hoffman and Misha Verinsky, I think, asymptotically provided a formula. So it's a very interesting thing to actually say anything new about the Euler characteristic of it. And so I've been thinking about it. So in the easiest cases, I think I can make those congruences also explicit for out of 10. Like, I think out FB minus 1 with the p torsion is just a simple p torsion, 1 is equal to p, and it's this, what do you call it? I don't know, like the rows, the p rows that shows up. So there is a formula in these simple cases, but well, these formulas they gave so far don't discover anything new because, well, these cases were also well understood by other groups. But in some examples, in some ranges, I'm looking at it actually right now. I hope that you can say maybe something new about this Euler characteristics of outer things as well, at least some fractional parts of it. And I mean, yeah, we'll see where it goes. But yeah, certainly one of my favorite examples to look at. Yeah, thanks for the question. Yeah.
Let us take some over 2D relevance, more consciously, or communicating with each other. It's reminded me a lot of counting formulas for character varieties, genus one, where you also have exactly a sum of this.
Yeah, I mean, all these things are, yeah, I mean, certainly related to that as well, because, I mean, yeah, I mean, even more related to that is probably the ones you asked about, the ones with the all community tuples without any p-powers and stuff like that. And some of the inspiration, I think, for Hopkins and Ravenel, consider these things came from these type of varieties. Yeah, that's what I believe. I mean, they even have some computation there of some Euler characteristics of some type of Grassmannians and things like that, which kind of generate these kind of community tuples. So there is some relation, but I'm no expert in it to give you an exact. Interesting. Yeah, yeah, I can show you this place where they do this.
No paper of T and Siegel, we first define the Aberdeen characters.
No, I think the Euler characteristic itself is defined by Volt.
No, the equity variance.
For space, that would be, yes, that would be. But I was actually today using one for space. So, yeah.
Have you tried other arithmetic groups?
Yeah, I tried the SL P minus 1Z. Well, they're nothing interesting because centralizers are virtual tori. So Euler characteristics going to vanish. So the SL does not give you much.
In your examples, this is a lattice in Hermitian group. Maybe is it something important for your examples? That
What do you mean?
SP is a lattice in SP to an R, which has infinite universal cover.
Well, that is important in my examples because the symmetric space of that thing is exactly the Zianda G. So it does play a role, that thing, of course, yeah. But I'm not explicitly using that somehow. I just use
No,
it.
my suggestion is to take a group with similar properties. So a lattice in another Hermitian group maybe.
Yeah,
So you're saying that maybe like the fact that these are actually fundamental groups of varieties rather than just.
yeah, yeah. I mean,
Either cohomology.
like this is how this whole arithmetic groups business works. That like all of these formulas, well, like these formulas, what I was talking about, that this is some data number. It's true for any arithmetic. That's true, yeah. So I could try out any arithmetic group if I wanted. That's true. The question is how much I can classify all these finite order elements in there. That's a different problem. So I do not know if, yeah.
Yeah, well, we will get back to Aberdeen. Talk with Ben. He might.
Yeah, he might help on this, yeah. So we'll see. I'll try it.
And more options. If not, then that's